In our walk across campus, or in our neighborhood, or even in our local park, we get the idea that the landscape is this ever-present, very static sort of background on which we live our lives. But the landscape is something more. It is a recorder of the dynamic forces that have acted to shape the Earth. I'm standing in front of the Sierra Nevada, the crest behind me. Mount Whitney rises to over 14,000 feet. It records the dynamic forces that are shaping the Earth.
Nowhere is this probably more evident at the Earth's surface than during a raging flood, where flood waters act to sculpt and shape the landscape and interfere with our daily lives. This awesome force shows us the power water has on the Earth's surface in sculpting the landscape. This unleashing the power stored in it from the sun. Flooding is part of a natural process, though poorly understood by most. The water can go from channelized flow to spread over an area of many, many square miles surrounding the channel. In terms of not understanding it, a lot of people see the relationship between something like torrential downpours and flooding. But there's a lag in the system. You have to understand that flooding occurs in a stream system that is an interconnected network of streams and tributaries, each tributary contributing sediment and water to the larger stream, which in turn may be a tributary to an even larger stream. Channelized flow will occur most of the time, but when the water volume exceeds the capacity of the channel, we get flooding. Now here, I'm showing a hydrograph of stream discharge, and above it you can see the duration of strong rainfall and rainfall intensity. The rain occurs and water starts to gather. Flooding won't occur until you reach a threshold called flood stage. Flood stage is the stage at which water breaches the channel. Rainfall can stop and water is still collecting in the stream system. Peak flow won't occur for many hours. So you're not necessarily safe once the water stops falling from the sky, but flooding will occur. And again, it is part of a natural system. It's part of the larger system of water flowing on the Earth's surface. The other thing that's poorly understood is the idea of a 50-year flood or a 100-year flood. And so I put this chart up to kind of make some sense of it. If you look at the annual maximum discharge, the discharge of any stream going through any specific area of the channel is the volume of water over time. Discharge is considered volume in cubic meters over time in seconds. As that increases during heavy rainfall, you can get flow that starts to flood, but how much flooding depends on the amount of water that's going into the system. When we talk about a 100-year flood, that means a flood volume that occurs only once every 100 years statistically. That doesn't mean if you have a flood in 2021 that you won't have an identical or larger flood in 2022. It is about a statistical averaging. And here you see the plot. The plot is a nearly linear relationship. And so even though a 100-year flood is not likely to happen 2 years in a row, it certainly could. During these flood stages, as you can see on the block diagram on the right, the normal stream flow is shown in the middle, but the water coming out of the channel now floods an area of the lowlands. How much flooding is going to occur depends on the discharge, that is, the volume that is coming through the channel at any particular moment in time. Flooding, although probably the greatest single example of the force of stream flow on the planet, it is part of a larger system. And it is true that in that system, sculpting the land mostly takes place during flood stage. But let's take a look at that larger system. Looking at water on the Earth's surface, we need to look at it as part of a cycle, the hydrologic cycle. Now, you have heard of other cycles. Perhaps in your biology class you may have heard of the carbon cycle or the Krebs cycle or the phosphate cycle. When in science we look at any system, and here we are looking at water flowing through the Earth system, when you look at any system, a cycle is looking how some material in that system moves by one process from a reservoir to another reservoir. In the carbon cycle, it may be from carbon in an apple to getting into your system to you taking that carbon and moving it around, and we're following. In the Earth system, when we look at water flowing on the Earth's surface, we're looking at a cycle where water is stored in one reservoir and through some process goes to another reservoir, and that process requires energy. And the energy driving the hydrologic cycle is the sun. In fact, surficial processes, these are the processes acting on the Earth's surface that are independent of the Earth's internal heat engine, are all solar powered. Now I know what you're thinking, waves on a beach, that's from the wind. The wind is driven because of differential heating of the atmosphere. It is solar powered. Now this becomes important because when we go further in this discussion, we're going to have to look at how the energy in that system is distributed. But for the moment, just know that solar energy causes evaporation. Now, if we start with the ocean as a reservoir, we have water changing phase from liquid to a vapor and going into the atmosphere. Side note, I ask students very commonly when I'm in the lecture hall showing this particular image, the water in the ocean is being evaporated and put in the atmosphere. Please point in the picture at the water in the atmosphere. Almost universally, they point at clouds. And that's absolutely wrong. The clouds themselves are the one place where you don't have water vapor. The clouds represent condensation of the water vapor in the atmosphere. Water vapor is a colorless, odorless gas that we are inhaling and exhaling all the time, putting it out into the system, taking it in from the system. But in the atmosphere, it is in with the other gases like nitrogen and oxygen, carbon dioxide, and others. When the atmosphere is too cold to hold that water vapor, it condenses out. And when you fly through a cloud, you're bumping around through water droplets, and in the upper part of the cloud, probably ice crystals. Now we take a look at this system, and it sort of leads to the idea of condensation. So when the atmosphere saturates with moisture, you get to a point where the atmosphere can't hold anymore, and it starts to condense out. The ability of the atmosphere to hold water vapor is a function of temperature. Warmer air can hold more water vapor than colder air. And that's what happens when water vapor getting into the upper atmosphere starts to cool. It condenses to form clouds. When there's more water droplets up there than updrafts in the cloud can literally hold, it's going to come raining down to the Earth's surface. Some of that water is going to go right back into the atmosphere through either evaporation, which is a physical process, or transpiration. Transpiration is when water vapor through biologic processes is exuded back into the atmosphere. I mentioned respiration. Everything respires, and that's part of what transpiration is. Sometimes in middle school, they put these things together and refer to evapotranspiration. There's absolutely no such thing. They are two very distinct and separate processes. Some of the water falling on the Earth's surface is going to infiltrate the ground. This infiltration is something that's going to give us groundwater, and groundwater is one of the reservoirs. We also have surface runoff. Most of that through channelized flow. And that's really what we want to focus on, because when we look at sculpting the landscape, it's going to be about this channelized flow. The reservoirs that we just looked at, we need to sort of think about a little bit more. One is the cryosphere. The cryosphere is the reservoir of frozen water on the planet. Most of the freshwater reservoir of the planet is locked up in ice. And we talk about ice here. We're looking at some sea ice, but in reality, we're talking about glaciers, either in alpine environments or in ice sheets. Most of the world's fresh water is locked up in glaciers. Now, we also have groundwater. Most groundwater, by the way, is in the pore spaces of rocks, sedimentary rocks mostly, where we have droplet after droplet saturating the whole zone. Occasionally, we have in areas of karst topography, we have some underground pools of water, but that's not what most groundwater is. But it makes for a much better picture. And then we have water on the Earth's surface, especially through channelized flow. What we see here is water moving on the Earth's surface. We're talking about water acting on the Earth's surface. And that's what we're going to discuss. We're going to discuss this idea of channelized flow and the energy that's being exerted by the moving, rushing water on the crust and surface of the Earth. And it doesn't matter whether we're talking about a small stream in your backyard, the waterfall we just looked at, or some large river. They all work mechanically the same way. They all obey the same set of physical laws. And they all respond to differential energy in the system. And that's what we want to do. We want to look at this by following the energy. When looking at the Earth's surface and how water sculpts the landscape, we do have to consider the energy. And to put this into some greater perspective, there are two kinds of energy that are important here. One is potential energy, or the energy of position, and the other is kinetic energy, the energy of movement. The energy of position will all be about where water is on the Earth's surface with regard to elevation. The energy that is kinetic will all be about stream currents and discharge and moving water carrying sediment down through the gorges of canyons and rivers cutting down into the crust of the Earth. Let's take a look at the difference between potential and kinetic energy with a quick visit to the International Space Station.
Welcome to the International Space Station. I'm astronaut Joe Acaba. Today, we're going to talk about potential and kinetic energy. Let's get started. Kinetic energy is the energy an object has because of its motion. An object can store energy based on its position. This is called potential energy. On Earth, imagine dropping an object from a raised position. As an object's altitude above the Earth's surface increases, its gravitational potential energy also increases. The potential energy stored due to its position is now being converted to kinetic energy. Here on the International Space Station, we are still under the influence of gravity, primarily due to our position with the Earth. So when I have this ball on this ramp, normally back on Earth, I release the ball and it rolls down the ramp due to a change in its potential energy that's being transferred to kinetic energy. But as you can see, it doesn't happen here. So it doesn't mean we don't have potential energy. It just means we're not converting it at this time to kinetic energy. And why is that? Gravity is pulling us down, but we're moving super fast, and so what it is we're bending around the Earth in this perpetual falling motion. Thanks for joining me on board the International Space Station. We're sending it back to Earth so you can try your own experiment. See you next time.
Back here on Earth, potential energy is the energy of position where precipitation maybe falls in a highland. And when you compare that elevation to where the water is going or the base level, then you get an idea about how potential energy is stored in the system. Here we're looking at the long profile of a stream, and long profiles of stream all have sort of the same basic characteristic. A steeper gradient near the head or source area, the beginning of the stream, and a much more gentle gradient as you get towards the mouth or base level. When we look at a comparison of the elevation difference, this is where potential energy is coming from. It's the difference in elevation between base level and headwaters. The greater that elevation difference, the greater the potential energy of the stream system itself. Now we can see this reflected in actions as that difference in elevation changes, and it can change for a number of reasons. One way it can change is through either a drop in sea level or an uplift of the source area, say through tectonism, an uplift of the mountains, that increases the H, or the elevation difference. It increases the potential energy. The greater energy means there will be more erosion throughout the system, and the long profile will adjust, and all of the crust of the earth between the former profile and the new profile, that's eroded material. Now the other thing can happen. We can have a change where, say we have subsidence of the land, or more likely, we have a rise in sea level as we're experiencing today. That would change the elevation once again and take less energy out of the system. Lower energy means there's less energy to carry sediment in the system, and therefore you will see an adjustment in the stream profile by filling that in with sediment. Now this can happen not only through subsidence of the land or the raising of sea level, but you can also get the same effect by damming part of the stream, because by damming part of the stream you essentially take the upstream area and change the elevation difference between the headwaters or the source and base level. The net impact of this energy is that it erodes into the crust of the earth and sediment is carried downstream. But to understand the evolution of stream systems, we need to understand where that energy is most concentrated. And let's be very clear about energy. No energy is going to be created or disappearing here, right? That's a basic law of the universe, that energy will not be created or destroyed through what we're seeing. What we're looking at is the energy available to do work on the geologic medium. If there is an excess of energy, then the work that will be done is erosion and transport. Material will be eroded off of the crust of the earth and carried down the stream. If the stream has less energy than it needs to carry sediment, then it will deposit the sediment. And these are things to remember as we look at how a stream system will work. But again, let's look at concentration. We've been looking at the Grand Canyon of the Yellowstone River, and this is Lower Yellowstone Falls, and it's a good place to look at this idea of energy concentration. Right at the falls, we could compare three locations. One is upstream of the falls, one is the length of the falls and base of the falls, and the other one is downstream of the falls. You could ask the question, where is the energy available to do work on the geologic medium most concentrated? And here we can see with an increase in current, you're going to have an increase in energy. And the face of the falls and the base of the falls is where the energy is going to be concentrated. This has a result we can predict. Waterfalls will preferentially have erosion because we have a higher concentrated energy. This will cause the falls to migrate upstream. Falls are ephemeral features in streams. We usually find them in youthful features. They are constantly under attack through stream erosion and are literally migrating back upstream. Now we can take this same question and look at the long profile of any stream and ask the same, where is the energy most concentrated? Well, let's look at three areas here. In the higher reaches towards the head or source area where we have a steeper slope gradient, somewhere in the middle, or somewhere in the lower reaches near the mouth and base level. The energy available to do work is going to be concentrated up near the steeper slope gradient. Now be careful here. The overall energy of the stream is mostly in the mouth of the river, Well, why isn't that doing erosion? The reason is most of that energy, if not all of that energy, is taken up moving sediment that's in the stream from upstream locations. In terms of the most energy available to do work, it's in the area near the headwaters or source. And it has a predictable impact on the stream, actually two. One is you're going to see headward erosion. Streams will lengthen through this process of headward erosion and differential erosion because of higher concentration of energy near the headwaters. The other thing we're going to see is because this higher concentration is related to the current, how fast the stream is flowing, preferentially, areas that are a little steeper will get ground down. And what we see is the second impact of stream erosion, and that's channel downcutting. So the thing to understand about stream erosion is that it's a function of the discharge rate. Remember, the discharge is the volume of water over time coming through some area of the channel. Running water is loaded with gravel and sand and sediment, and this is the agent of erosion here cutting down into the crust. And do remember, it causes two impacts. One is headward erosion, which will lengthen the stream, and channel downcutting. Take a look at the channel here. This is a youthful stream, and in a youthful stream we don't see any floodplain, we don't see a lot of meanders, we see a relatively straight course and a very V-shaped canyon. This is typical of youthful streams. Well, if that's typical of a youthful stream, why is it mature streams look like this? When we look at the elements of a mature stream, what we notice is there's a main channel that's meandering not through a canyon anymore. The canyon has mostly disappeared and it's meandering through a large floodplain. When we look at these meanders along the stream, we'll see that there's a cut bank always on the outer portion of a curve in the stream, and something called point bar deposits. These are like beaches that form with mostly sand, but could also be gravel, on the interior curve of these meanders. We also find cut-off meanders that form lakes such as this one that can be referred to as an oxbow lake. To understand what happens to the stream canyon, you have to understand the formation of these meanders.
The meandering rivers of the plain are tame and lazy, but mountain streams are corralled by the steep walled valleys they carve. Their courses are literally set in stone. Out on the open plains, those stony walls give way to soft soil, allowing rivers to shift their banks and set their own ever-changing courses to the sea, courses that almost never run straight. At least not for long, because all it takes to turn a straight stretch of river into a bendy one is a little disturbance and a lot of time. And in nature, there's plenty of both. Say, for example, that a muskrat burrows herself a den in one bank of a stream. Her tunnels make for a cozy home, but they also weaken the bank, which eventually begins to crumble and slump into the stream. Water rushes into the newly formed hollow, sweeping away loose dirt and making the hollow even hollower, which lets the water rush a little faster and sweep away a little more dirt, and so on and so on. As more of the stream's flow is diverted into the deepening hole on one bank and away from the other side of the channel, the flow there weakens and slows. And since slow-moving water can't carry the sand-sized particles that fast-moving water can, the dirt drops to the bottom and builds up to make the water there even shallower and slower, and then keeps accumulating until it becomes new land on the inside bank. Meanwhile, the fast-moving water near the outside bank sweeps out of the curve with enough momentum to carry it across the channel and slam it into the other side, where it starts to carve another curve, and then another, and then another, and then another. The wider the stream, the longer it takes the slingshotting current to reach the other side, and the greater the downstream distance to the next curve. In fact, measurements of meandering streams all over the world reveal a strikingly regular pattern. The length of one S-shaped meander tends to be about 6 times the width of the channel. So little tiny meandering streams tend to look just like miniature versions of their bigger relatives. As long as nothing gets in the way of a river's meandering, its curves will continue to grow curvier and curvier until they loop around and bumble into themselves. When that happens, the river's channel follows the straighter path downhill, leaving behind a crescent-shaped remnant called an oxbow lake,
or a billabong.
O un lago en herradura.
Ou un bras mort.
We have lots of names for these lakes, since they can occur pretty much anywhere liquid flows, or used to. Which brings up an interesting question. What do the Martians call them?
So when we think about what happened to the canyons that the streams used to be in, the story is in the formation of the meanders and the continued development of the meanders. Let's kind of review this through the lens of energy. When you think about a curve in the meander, you look at the cut bank on the outside, the main channel, and the point bars on the inside of the curve. And you ask the question, what has the most energy to do work on the geologic medium? And that's all about the current, how fast the stream is moving. And if you think about that, the stream on the outside is moving faster. Think about children on the ice playing a game called Crack the Whip. If you're not familiar with it, don't try this at home or on your own, but a child in the middle grabs a friend next to them, who grabs a friend next to them until you have a long chain, and the person in the middle, the child in the middle, is turning very slowly. But by the time you get to the person at the end of the chain, they're moving very quickly to keep up on the outside of the curve with what's going on the inside of the curve. And that's because they have to travel farther in the same amount of time. The same thing is true in the stream. As the stream goes around that meander, the erosive forces on the outside of the curve are what are forming the cut bank. Now imagine these meanders moving back and forth and sweeping into the edge of the original canyon that the stream was in. Over time, that canyon will erode and widen, and eventually you will have a plain that the continuingly to mature stream will meander across. Here we can see that system, the fastest moving water being traced around through the meanders with point bar deposition. Why? Lower current, less energy, not enough energy to keep the sediment in transport, and it deposits. On the outside, more energy than is needed to transport the sediment to the stream, and it's eroding. When we look at a stream channel in low flow, we can see that the energy really is concentrated there in the size of the clasts, the fragments that are moving in the bed load. Here you can see the gravel, and this is where we will find gravel and sand. For the most part, is right in the channel of the stream. Now, if there's enough energy, that bed load gets moved along. When a stream slows down and a channel has more sediment than it can carry, what you will get is something called a braided stream deposit. Here are the braided streams. There's so much sediment in this channel that depositional bars are forming and the stream kind of braids around it. And this gives us a very important underlying principle. A stream system is carrying a sediment load. When it's in true equilibrium, there's just enough energy in the stream to carry the sediment load that it's carrying. When there's more energy than is needed to do that, it will erode. It'll erode the geologic media around it. If there's not enough energy to carry the sediment, it will drop sediment out until there's just enough energy to carry the sediment it has. Stream networks will form from the erosional properties of streams. Here's a typical stream network on the planet, and it has sort of a tree-like look to it, from which the name dendritic drainage is derived. And it has a random pattern of interconnected tributaries contributing water and sediment to a larger stream, which in turn contributes water and sediment to an even larger stream. And these dendritic patterns can be found everywhere where streams are just allowed to erode on their own. When you see dendritic drainage, it suggests that the stream really is eroding under its own nature. Occasionally, we see other kinds of drainage patterns. Here in Pennsylvania, we are looking at the Susquehanna River. It has something called trellis drainage. If you look, there are valleys that are at right angles to the Susquehanna River. Each one of those has a small tributary that feeds into the Susquehanna River. What's controlling the development of this drainage network is the geology. Each of the ridges of the intervening valleys are there because the rock of the Earth's crust here has been greatly deformed and tilted. And the more resistant to erosion layers are forming the ridges, and the less resistant layers in between are being eroded down to form the valleys. In turn, this dictates the nature of the network of tributaries interconnected to the larger stream. We also find areas where some high peak of topography will dictate the formation of the drainage network. Here, we're looking down at Mount Rainier. We have something called a radial drainage pattern. If you look, you can see all the tributaries from Mount Rainier are radiating out away from that single high peak. Here again, the drainage network, the stream system, has not evolved on its own. It's evolved under the control and influence of the topography of Mount Rainier. Where drainage networks are the erosional aspects of a stream, and when we're looking at how the landscape is being altered, we do focus a lot on the stream erosion. But streams are carrying sediment, and that sediment will eventually deposit. Usually, what we find is they deposit in deltas. Here is the Mississippi River Delta, where the Mississippi River flows out into the Gulf of Mexico. This kind of delta is referred to as a river-dominated delta. And of course, all deltas are there because the amount of sediment that is being brought down to the marine environment by the river is outpacing the wave energy in the marine environment to remove and mobilize that sediment. Here, in a river-dominated system, it's so outpacing it that the river system itself forms a delta that builds out into the marine environment. You can literally see what some people refer to as kind of a bird's foot, where the channels and distributaries can be seen building out into the marine environment itself. Here we're looking at another delta from space. This is the Nile River Delta, and it is the quintessential delta for which deltas are named after the Greek letter delta, which is a triangular-shaped letter. And this kind of delta is referred to as a wave-dominated delta. Even though what's happening is the river system is putting more sediment into the marine environment than it can carry away, the shape of the front of that delta is being modified by high wave erosion, and that's where the term wave-dominated delta comes from. And here's a third and final kind of delta. This is the Colorado River Delta, where it flows into the Gulf of California. What you see is sort of a cuspate inward delta where we have depositional bars, major depositional bars, that are forming right at the mouth of the river. This is referred to as a tide-dominated delta. And it doesn't mean that the tide literally is moving things in or out. What the tide does in the marine environment is change the position that wave erosion can occur. And because of the high tidal range in this area, it allows wave erosion to work way back into the mouth of the river, forming this very distinctive tide-dominated delta. Anywhere where energy in a fluid system slows down and there isn't enough energy to carry sediment, you start to build up depositional features. We are going to see that next in our studies when we study environments of climatic extreme, places like desert or glacial environments. Here in a desert environment, we form a depositional feature referred to as an alluvial fan. It is a fan-shaped feature at the mouth of canyons that have eroded in the desert environment. These form not from stream flow per se, but from debris flows, from flash floods and debris flows that form during heavy rainfall periods in the desert that act to shape the desert and leave this distinctive feature we refer to as an alluvial fan.
So we've been looking at how the Earth's surface is sculpted by secondary processes that overprint tectonism and volcanism. We're looking essentially at how water acts as an agent of erosion to sculpt the landscape. What we're going to do in our very next lecture is start to discuss how surficial processes differ in environments of climatic extreme that also act to shape the Earth.